Good morning, everybody. Welcome back. Why is this missing? Let's see. All right. Let me share my screen right quick. We're gonna finish out this handout dealing with partial pressures. We're gonna finish that out. I think we've already discussed, yes, Hess's law. And the last thing we're gonna talk about is the partial pressures. And then we have one more lecture that'll take place between today through Monday, and then we'll be done. I know it's crunch time, but it's crunch time for everybody. So, yeah. So let me share my screen right quick, and we're going to talk about partial pressures today and Dalton's law. All right. So let's just discuss this real quick, and we're going to do some examples of Dalton's law of partial pressure. And so this moves us into a different area. We've been talking about Hess's law. We've been talking about enthalpy and entropy. So this is a kind of a slightly different area. But we're going to talk about now is we're going to move into what is typically described as the gas law or the ideal gas law. Right. And so one of the things that we have to discuss before we get to that is this idea of what we call partial pressures. So if you have a mixture of gases, let's say you have a canister that has a mixture of oxygen and nitrogen or and chlorine gas, what Dalton's law states is that each gas has a specific, what we call partial pressure. And each gas had those partial pressures add up to the total pressure, right? So if you have, for example, if you have N2, O2, and Cl2 gases, each one of those is going to have a specific pressure associated with it. And when you add those up together, you're going to get the total pressure. Right, so each gas has its own pressure, which is a partial pressure, and then that's going to give you a total. So over here where it says P total, that's going to equal the pressure of N2 plus the pressure of O2 plus the pressure of Cl2. All right, and that pressure is related to other factors. It's related to the temperature, it's related to the volume, it's related to the number of moles. And so that's how we're going to develop this idea of what we call the ideal gas law. And I'll show you that in a second. You probably remember it from high school, but I'll show you that in a second. So there's another piece to this, which we call the mole fraction. And that is what fraction of those gas molecules make up like a specific sample, right? So we have again, a 3-gas sample like we have shown N2O2 and Cl2. The question is how many moles of each one are in there. So the mole fraction doesn't have units because it's a percentage. Basically, it's a total moles of A divided by the total number of moles. So in this case, we have the example given here is for a 2-gas sample, but let's say for the sake of our discussion, we're going to say let's look for the number of moles or the mole fraction of Cl2. That's going to be the moles of Cl2 over the total, right? So moles of Cl2 N2 plus O2, right? So that mole fraction can be easily calculated if you know the number of moles of the gas or the gases in question, right? Sometimes you can solve for it, other times you can just calculate it. So the way you relate mole fraction here and partial pressure here is through this equation. The mole fraction times the total will give you the partial pressure of that particular gas, right? So what A is one of your gas, one of your gases. So it can be chlorine, nitrogen, or oxygen, depending on which one you're looking for, right? But there's another expression that we're going to also use to relate the number of moles of gas and the pressure, and that is using the ideal gas law, right? And that gives the relationship between all of the factors that control the pressure, right? So it's PV equals nRT. So N is the number of moles, right? R is the gas constant. T is the temperature. And that's in Kelvin. And then, of course, pressure and then volume, right? So all these things kind of work together and you can solve for any of these. To get the R is a constant, right? You know that that number, I'm going to give you that number, but that number is a given, right? It's a constant. So you will never have to solve for that, but you can solve for the number of moles, you can solve for the temperature, you can solve for the volume or the pressure by rearranging this relationship. All right. So let's take a look at some examples. All right, because gases are not ideal, but a lot of times in order for us to study certain things, we have to make some assumptions. And so we have to assume that things are behaving in a certain way, and so on and so forth. So your pressure, let's talk about that. So the pressure can be in atmospheres. It can be in torr, right? Pressure has a lot of different units that you can use to solve for. So a lot of these questions, they end up having conversions involved where you have to go from atmosphere to torr or millimeters of mercury. That's another pressure unit. Your volume is always going to be in liters. Of course, moles are moles. There's no units for that other than moles. But then your temperature has to be in Kelvin, right? And if you remember from way back when we first started, Kelvin is 273 plus whatever your degree, if you have degrees Celsius, 273 plus that. All right. Any questions so far? Right. So with the ideal gas law and Dalton's law, what we assume is that the volume is negligible. We assume that gas particles have the same size. We assume that they move randomly, and we assume that every time the gases collide, there's no energy loss. So we're not. But what I want to do is take this and apply it. All right. So it says, let's go and apply. Let's take the Dalton's law example first, and then we're going to do some ideal gas law example questions. Right. So here, with the first Dalton's law example, it says calculate the partial pressure of an air sample containing 0.76 grams of N2, 0.24 grams of O2 when the volume is at 1 liter and the temperature is at 20 degrees Celsius, right? So we can find the partial pressures of each one using the ideal gas law. Right, and we can talk about the R here because R is going to be dependent upon the units of pressure, whether it's atmosphere or millimeters of mercury or whatever. Each there are multiple R values depending on what units you use. All right. So for here it says find the partial pressures using the ideal gas law. So we can find the pressure of N2, right? By rearranging, again, let me give you this PV equals nRT. So we can rearrange this to find the pressure by dividing both sides by V. So P N2 is nRT over V. Now, if you notice in the question, it says we have 0.76 grams of N2, right? But we need N right here to be what? N needs to be in moles. So how will we convert 0.76 grams into moles? All right, so wouldn't that just be grams over molar mass? Right, that'll give me moles. So I can take that 0.76 grams and divide it by 28 grams per mole. Right, because here we have N2 and each nitrogen atom is 14 grams per mole. So I can just divide this by 28. And that's going to give me the moles of nitrogen. By the same token, for oxygen, I have 0.24 grams of oxygen. And I can just divide that by 32 grams per mole because there are two oxygens here. Right, and that'll give me moles of oxygen. All right, give me moles of oxygen. So I need the moles, and I also need, it gave us the volume for both is 1 liter. All right, so we know that. And then we also know the temperature, 20 degrees Celsius, which we have to convert into Kelvin. Right, so that's where all our numbers are coming from down here. So 293 Kelvin is 20 degrees Celsius plus 273. That's where the 293 comes from. The 1 liter is the volume, and it's the same for both. And then the moles of nitrogen and the moles of oxygen, we just calculated up top. That's where those numbers are coming from. And then here, this is the last thing we want to talk about, which is R. Right, R is what we call the gas constant. Right, R has many values. It just depends on what pressure units you're working in. All right, let me give you a couple of the other values for R. Right, so if you're working in atmospheres and liters, then this is your R value, 0.0821 atmosphere liter per mole Kelvin, right? And you notice the units are all cancelable, right? You got Kelvin, you got liters, and all that's going to cancel, and you have moles, and that's going to cancel and leave you with atmospheres, right? If your volume is in cubic meters, right, you can use this R value. It is 8.2057 cubic meters atmosphere per mole Kelvin. Because cubic meters is a unit for volume, right? If your pressure is in torr, right, and this is the pressures in atmospheres. If your pressure is in torrs, then R is going to be 62.3637 liters torr per mole Kelvin. And it's the same if your pressure is in millimeters of mercury. So your pressure units can be atmosphere, torr, or millimeters of mercury. And if it's millimeters of mercury, it's going to be the same, 3637 liter millimeters of mercury per mole Kelvin. All right, so these are R values, and again, it's going to vary based on your pressure, or it can vary even based on your volume unit. But more than likely, the pressure unit is what's going to be different. So that number can change. But once we put the numbers into the calculation, we see that for N2, right, the partial pressure for that is 0.65 atmosphere. And then for O2, which is here, the partial pressure for that is 0.18 atmosphere. And then the total pressure is 0.83 atmosphere. right? Any questions about that? So what we did was we took the ideal gas law and we rearranged it so that we could find the partial pressure based on the number of moles, the temperature, and the volume. And that's really, with that ideal gas law, that's really the key, is to learn how to rearrange it. So let's go back up to it. Right, if PV equals nRT, if I want P, I can rearrange that. I'm just going to abbreviate that as IGL, ideal gas law. If PV equals nRT and I want P is nRT over V. If I want V, it's nRT over P. All right, if I want T, it's going to be PV over nR is T. I mean, anything that I want, if I want N, it's going to be PV over RT is N. I can solve for any one of these variables. It doesn't matter. All right. So if I want to rearrange that, I can rearrange it and solve for any one of the variables. It doesn't matter. All right, let's look at another example in B. Are there any questions about the example we just looked at? All right, so B says that sample of air is heated until the total pressure is 1 atmosphere. So we know the total pressure. What are the partial pressures of the two gases? Right, and so we need to solve for the partial pressure of each of the gases. But remember, it says the sample is heated until the total pressure is 1 atmosphere. So you got two gases starting at room temperature, and then you heat them until the pressure is 1 atmosphere. So let's look at it. All right, so it's the same, it's part B of this example. So this sample is heated. So right here, it says to use the mole fraction to find out what the partial pressures of the gases that are heated to 1 atmosphere. So remember, the mole fraction is, so here Xn2 is the moles of N2 divided by the total number of moles, right? And that is 0.783. And then the mole fraction of oxygen is the moles of oxygen divided by the total number of moles. So again, a mole fraction is like a percentage, right? So we're going to do this, right? And now at 1 atmosphere total pressure, this is the mole fraction. These are the mole fractions at that new pressure, right? So now I just need to take that and find out the partial pressure of each, because up here we said that the mole fraction times the total pressure will give us the partial pressure. So once we figure out the mole fraction, we know the total is 1 atmosphere. So let's go back to here. All right, so we know the mole fraction times the total pressure is the partial pressure. So we're going to do that for each one. So XO2 times P total is PO2. So it's the partial pressure of O2. All right. So that's what we did here. So we took the mole fraction of N2 times 1 atmosphere. Obviously, that's not going to change the number. And then that gave us 0.783 atmospheres. And then the partial pressure of O2, which is the mole fraction of O2 times the partial pressure, the total pressure of 1 atmosphere. So that's one application, right? We could find the total pressure of the sample by finding the partial pressure of each gas at a certain temperature. And then the B part of the question says, if you heat it up and the total pressure increases to 1 atmosphere, because you see right here, it was 0.83. So it says, if you heat it up and the total pressure is now 1 atmosphere, what are the partial pressures of the gases? And we can use, again, the mole fraction that we talked about earlier. So mole fraction times the total will give me the partial of any one of the gases that make up that sample. All right, any questions? Any questions right here? All right, let's see if we can pull up one more example. And then I'm actually gonna introduce the next topic. I haven't put the handout for that on Blackboard yet, but we're just gonna discuss it. Let's pull up one more example. All right, so in this example, we're going to calculate the partial pressure for each gas in a sample. So it says dry air contains 78.08% nitrogen, 20.095% oxygen, and 0.95% argon. And the question is to calculate the partial pressure of each gas in the sample. All right, at 760 torr. All right, so you can do this a couple of ways. You can leave the pressure as is in torr and use that R value for torr, right? Or in this case, it doesn't give us a volume, so what we can do is figure out the partial pressure based on the percentages. All right, so we could say that the percentages is 78.08, 20.095, and 0.95. So we can take that and we can use those numbers kind of as a mole fraction. So let's do that. We can use the percentages as a mole fraction, right? So 78.08% is the same as 0.7808 moles of N2. And then we can say 20.95, if we assume 100 moles. Mm-hmm. All right, so sets, and then the 20.95 we'll say is 0.2095 moles of O2, and then the 0.95%. Argon, we'll say, is 0.0095 moles of argon. Right. And so we can say that now, if we know the mole fractions and we know the total pressure, we can calculate the partial pressure of each one. Because remember, the mole fraction times the total pressure is the partial pressure. So let's say AR, and then X N2 times P total equals P N2, the partial pressure of nitrogen, and then the mole fraction of O2 times P total is PO2, the partial pressure of O2. So we can just take that and we can say 0.78, I'm sorry, it's 0.0095. There are no units here, times 760 torr. Then for N2, we can say 0.7808 times 760. And then we can say here, 20.9, 0.2095 times 760. Right. And that'll give us the partial pressures for each one. All right. And if we wanted to convert that to atmosphere, what we can do is the conversion, which is 1 atmosphere is the same as 760 torr. And generally, when we think about the partial pressure and or the pressure period, 1 atmosphere is like, that's regular pressure. That's like the pressure in the room right now. So that's one way to apply that. And it's a little bit different than what we looked at because we took the percentages and turned them into mole fractions. All right, questions about that? All right, let me stop here. I need to pull this other handout. Let me grab it. Sent it to myself the other day. Let's see. Too many emails. So, all right, and I know this is kind of jumping around topics, but these are my goal is to hit like the important topics that you're going to need to carry forward with you in part 2. So we spent a lot of time on the other areas, but these areas you also need to have some familiarity with as well. So we're going to look at that too. All right. And I'll post this handout to Blackboard after class is over. All right, so the next topic is dealing with light and the electromagnetic spectrum. We're going to spend some more time here, and then hopefully between Friday and Monday, we'll work through some examples with partial pressures, and we'll also work through some other examples using light and calculating like the energy of a photon and things like that. All right, and this is the 20. All right, so when we think about and the reason why light is important is because the light and the emission spectrum of a particular atom was one of the ways that the structure of the atom was discovered. All right. So when we think about the atom and what is made of, the nucleus with protons and neutrons, and then the outside the nucleus where the electrons reside, a lot of that was discovered by studying the emission spectrums of certain, or the emission spectra of certain atoms or substances. So we have like certain substances that are going to give off what's called spectral lines, and every atom has a unique emission spectrum. And so when you look at the emission spectrum, it allows you to determine a lot of things about that atom. That's more specifically, it allows you to determine its electronic structure, like how many electrons are there, how the shell's oriented, so on and so forth. And we need that information, right? Because the makeup of the atom is going to determine how it reacts, like how the reactivity of it. If it's depending on what type of atom or substance you're working with, the number of electrons, the number of protons and neutrons, all of that matters. That's going to help determine the reactivity, right? Because a lot of times when we think about atoms, we just think about them and studying them on paper, but chemistry is, much deeper than that. There are a lot of things happening between atoms colliding and reactions happening, but we also need to understand past just the collisions, like what causes certain atoms to be attracted to other atoms, what causes certain atoms to react in a certain way. So when we think about light, right, you can bombard a sample with energy, and that sample is going to give off, like this is an example of a spectrometer where you just hit a specific sample of a substance with energy, and it gives off light, and then you have a prism, and then you have a recorder, and the prism obviously is here. So the light hits the prism, and then that light is um, fractured, and then you see different colors in a particular spectrum, right? For human beings, we can only see what's called a visible spectrum, right? So that's between a little bit between infrared and UV. There's a gap between those two, and that's the visible spectrum. And I'll show you that in a minute. Um, but when we think about light and what it's composed of, light is actually, well, it has a couple of definitions, but it's actually a combination of both electric radiation and then magnetic radiation. So when we talk about light, that's what we call it. We call it electromagnetic radiation, right? Because it has an electrical component and it has a magnetic component. So you got this oscillating wave of both electric fields and magnetic fields together. And that's what happens when you move a charged object, like an electron or like, a subatomic particle. When that happens, then you generate this electromagnetic radiation. So here's an example of what that looks like right here. I'm gonna come back up top, right? But here's an example. So you have your magnetic field, which is in purple, shown here. And then you have your electric field, which is the different waves that are in orange, right? And so when you think about light, light has a specific frequency and it has a wavelength. And if you remember if you took physics in high school, the wavelength is the distance between two peaks on a wave. And then the frequency is how many times one of those peaks passes by a certain point. So every um, all electromagnetic radiation is going to have a certain frequency and a certain wavelength, right? So over here, when we have frequency, is measured in hertz because it's a measure of the number of times per second of the peak on that particular wave passes through a certain point, right? So that's why the units for met for frequency is in hertz, and it is 1 per second. The number of times it passes a specific point is called its frequency. And then the wavelength, again, is the distance between the waves. So when you look at the wavelength here, which is given by lambda, this is just the distance between the waves, right? So wavelength and frequency have a really interesting um, relationship, right? Because all light travels at the same speed. You've heard this before, right? The speed of light is 3 times 10 to the 8th meters per second, or 1.86 times 10 to the 5th miles per second. I thought about this. I was reading a book about it's called Range. And in the book, it talked about how, we're building these spaceships, and, Bezos is building rockets, and Elon Musk is building rockets, and SpaceX, and they're trying to get to space, and they want to get off the earth and get somewhere far away. But in reality, I think the closest galaxy to the earth, the closest galaxy with another planet in it that's similar to earth, is something like 4 light years away. And that would take, if you're traveling at the rate of a regular rocket, which is about 20,000 miles per hour, that would take, I think he said, 130,000 years to get there. Light is traveling at 1.86 times 10. So let me give you that number. That is, so that's 186,000 miles per second. So you can calculate how many miles per hour that is by I think it's 3,600 seconds in an hour. So you'll put that in the top. I mean, yeah, divide that by 3,600 and you'll know how many miles per hour that is. But the point is that, all the race to get to outer space, and we're not going to get very far. Again, the closest exoplanet to us is 4 light years away. And that's traveling at a rate of 20,000 miles per hour, which is the top speed of the best rocket that we have. It'll take us over 100,000 years to get there. I just thought that was interesting because unless you can build a craft that can travel at the speed of light, it ain't happening. All right. So light travels at the same speed. And so the way we relate wavelength and frequency, and the wavelength is a distance, so that's in meters, right? So the way we relate that is through this equation. Right? So wavelength and frequency are related through here, where the frequency will be c over lambda, or the wavelength would be c over the frequency, where c is the speed of light. Right? And so when we take those two together, we can always solve for one or the other because we know the speed of light, that doesn't change. That's always going to be 3 times 10 to the 8 meters per second. And frequency is always going to be per second. And so when if we relate this equation right here, this is, let's just say 3 times 10 to the 8 meters per second divided by the frequency, which will move to the top and cancel. So your wavelength is going to be in meters. Right? So you can always solve for the wavelength, or you can always solve for the frequency. Typically, your wavelengths are measured in nanometers, which is 10 to the 9 or 10 to the minus 9 meters. And your frequency is typically measured in hertz. And if you look at the relationship between them, you can see that the frequency and the wavelength are inversely proportional, right? So the wavelength is equal to 1. We can just say 1 over the frequency, right? So they're inversely proportional. So if you have a shorter wavelength, that means that the frequency is higher, right? So when this number goes up, this number goes down, because high frequency and short wavelength, we're going to see that when we start talking about the energy. High frequency and short wavelength are both higher energy. If the wavelength is longer, then that means that the bottom number here for frequency is smaller. Low frequency, long wavelength, that means that that light has less energy. So the energy is going to be based on both the wavelength and the frequency. So we're going to pick that up on Friday. We're going to talk about how light and energy and how they're related and how we can relate that to quantum mechanics. We're not going to go into a quantum mechanic discussion because that's way past the scope of the class, but yeah, so we're going to pick this up on Friday. And I know we're jumping around, but we're going to hit the high points. So we need to discuss electromagnetic radiation. We talked about the gas laws, and then we've talked about entropy, the thermodynamics. We talked about that already. So what we'll probably do on Monday is just kind of work through some examples of each one of those, just to make sure that we see it in application and not just see it as a me just running through a PowerPoint. All right, and I will post this to Blackboard in the course notes section, so you'll have it for Monday, and then we'll just pick up where we left off on Friday. I'm sorry, so you'll have it for Friday, but we'll pick up where we left off. All right, any questions?
Thank you. Have a good day.
All right, y'all take care.
Dr. Russell?
Yep.
Would it be okay if we could set up some time to talk this week?
Yeah. Hold up, man. See who I'm talking to. Oh, Cal. All right. Yeah. I'll have some free time tomorrow. I don't have a lab tomorrow, thank God. I don't have a class until 6 p.m. So just let me know. Just text me. You have my number, right?
Yes, sir.
Yeah, just text me and let me know, and we can get together. I'm gonna send out an announcement too, because I got all the averages calculated and all that stuff. So if that's what you're referencing, then we can talk about that too.
Okay.
All right. Thanks, man. Have a good day.
You the same.
All right.